So far, we've considered only the regression case for linear modelling, that is to say, modelling continuous outputs. Now I'd like to look instead at the problem of classification. And for the time being, we'll restrict ourselves to the binary classification case. So there are two classes, and the labels can be 0 and 1. If we want to use a linear model to address this problem, well, one thought would be that we could just treat the zeros and ones as numbers and fit directly by ordinary least squares regression. People do occasionally do this, but it is generally not a great idea. One of the issues is that the outputs from linear regression are not just continuous, but they're also unbounded. They can take on any value from minus infinity to plus infinity. What are we supposed to make of these kind of values in the context of a problem where the answers can only have the values of 0 or 1? Well, one possibility, which we discussed in the first week's lectures, is that we can use thresholding to convert from the predicted value to the 0 or 1. We declare a threshold of 0.5. Anything that's above that we classify as a positive example, a 1. Anything that's below that we classify as a 0. Let's have a look at a simple example where we do exactly that. Here is a plot of some data which we're going to use in a 1D binary classification problem. So there is a single input feature x, it has continuous values, some of which are shown here, and the y values, the labels are either 0 or 1. In fact, we can see here that the problem is very simple. Anything that is above 0 has been classified as a 1, anything that's below 0 is classified as a 0. If we try to fit this by ordinary least squares regression, we'll get a line through the data that looks something like this. If we do our thresholding at 0.5, the results are as you can see. The fitted boundary value is not 0, which is the true value, but somewhere a bit higher. So far, so good. The boundary is not quite right, but no, nobody's perfect. Let's imagine that we now add one more data item, which happens to be positive, and it's over here. This time when we fit, the line has a shallower slope because of this additional positive example, which has a higher input value. This shifts the threshold even further to the right. So somehow, adding an additional value which is even more definitely correct has made our predictions worse. This is a reflection of the fact that what we're actually looking for is not this sloping line, but the vertical line which truly separates the two classes. We don't really care how far into the positive class a particular example is, but that problem is not well captured by fitting the linear regression model. What this comes down to is a reflection of the fact that classification and regression, despite some superficial similarities, are actually solving somewhat different problems. In a regression problem, we are looking to find a hyperplane, in the case of a linear model, or more generally, a manifold, which unites all of the data points, all of the data samples live reasonably close to that plane. In the classification problem, we're looking for a hyperplane or some other form of boundary which divides the data. And in fact, ideally, none of the data should live on that boundary. It should all be well away from it. The two problems are, in a sense, reciprocal to one another, or dual. In regression, we are actually interested in the hyperplane that we're fitting, whereas in classification, we are instead interested in the two half spaces that hyperplane divides the feature space into. Mean squared error, or the residual sum of squares, is not a good loss for solving the classification problem, for several reasons. First of all, it's symmetric. It will consider an error in one direction to be just the same as an error in the other direction in distance terms. But we don't really care about distance. Being further into the correct classification is still just being the correct classification. Being any amount of distance into the wrong classification is still completely wrong. So these two cases are not symmetric. The residual sum of squares, because of the square term, also gives more weight to outliers. It thinks that things that are further away from the boundary are more important and will move the boundary towards them. Again, we don't care about that because that's just an issue of distance. What we want is for things to be on the right side of the boundary, and that's all. This comes down to the question of how we are interpreting the continuous outputs from the model. We don't consider distance away from the boundary to be a bad thing. Perhaps there's some other interpretation we could place on it that captures that more reasonably. For example, we might think distance from the boundary is in fact a good thing and interpret it as a confidence in a prediction. Things that are very close to the boundary might be difficult to decide, and we might not really be sure what class they are, but things that are far away are very definitely a 0 or a 1. When it comes to defining a boundary, it seems like a linear model is actually a pretty good idea. As in the regression case, it's easy to frame and easy to understand. We can nicely express it in similar terms to the ones we used for the regression problem, where we have a vector of weights that defines what the separating hyperplane is. We then associate that with a decision function. In the initial example, where we were using regression to try and fit the zeros and ones, we suggested a threshold of 0.5. That seems a little arbitrary. In fact, the threshold could be anything, but it's often convenient to just select the threshold as 0. Then we can say anything that comes out of the model that is positive suggests that it's a positive example. Anything that comes out of the model that is negative suggests that it's a negative example. So we wind up with a simple decision function that looks like this. Given the clear inappropriateness of fitting this with the residual sum of squares, the mean squared error, the question is, can we come up with some alternative loss that better captures the kind of problem that we're actually trying to solve? So one very intuitive loss function is known as the 0, 1 loss. It looks like this. It literally just tells you whether or not your answer is correct. This is typically what we really care about. It's just the classification accuracy. However, it's non-convex, it's not differentiable, and it's hard to optimize as a result of that. The total loss is just a sum of step functions. It has a gradient of 0 everywhere except anywhere it matters, where the gradient is undefined. This metric of 0, 1 loss or classification accuracy is certainly very useful and important, and we'll come back to it, but it's not relevant to the problem for today. What we'd like instead is something smoothly varying, a continuous and differentiable function that somehow captures this idea of being mostly 0 or mostly 1. One thing that might occur to us in this context is to recast the model outputs as probabilities. These are continuous values, and they're in the range of 0 to 1, and they're very easy to interpret when making a prediction as saying we think it's this amount likely that this particular example is positive or negative. So if we want to think about this probabilistically, we're looking at a situation where the outcome is either 0 or 1. There are only 2 possibilities. It's like the toss of a coin or a Bernoulli trial. We'd like to define some function of the input vector x which outputs this probability. Let's say it's the probability of a positive outcome. The probability of a negative outcome will then be 1 minus the output of this function. We would like to use a linear function for this. We were talking in terms of linear decision boundaries. The problem is that linear outputs are continuous and unbounded, whereas probabilities need to be constrained between 0 and 1. There are a number of ways one could approach this. The way that we're going to use is to apply what's sometimes known informally as a squashing function, specifically this function here, called the sigmoid or logistic function. This has the effect of compressing the entire domain of real numbers into the 0 to 1 interval in a smooth and symmetric way. The compressed values relate to the original linear hyperplane in an intuitive fashion. The 0 threshold that we wish to apply to the decision boundary gets mapped to a probability of 0.5. If we have a very confident positive prediction, that is to say, the output of a high positive number, that will be mapped to very close to 1. Whereas a high magnitude negative number, that is a confident prediction that the sample belongs to the negative class, will be compressed to a value very close to 0. The slope of the linear hyperplane will control the steepness of the curve between 0 and 1, and changes in the linear offset, that is to say any fitted bias term, will shift the decision boundary. And with this sigmoid squashing function, we can now define a legitimate probability for our predictions that is constrained between 0 and 1. There are two cases. The probability that a particular sample is positive, conditioned on x, and parameterized by w, is given by the sigmoid of x dot w. Probabilities have to add up to 1, so symmetrically the probability that the same sample is of the negative class is 1 minus that sigmoid prediction. Given that the ground truth values y are always exactly 0 or exactly 1, we can use a notational trick to combine both of these probability cases into a single expression. The trick is that raising the prediction to the power of 1 leaves it unchanged. Raising a prediction to the power of 0 turns it into 1. When you multiply those two things together, one of the probabilities survives and the other one drops out. If y is a positive example, then the first term in the product survives. If y is a negative example, then the second term does. As in the linear regression case, we're going to assume that all of the samples are independent. Consequently, the probability of the entire training set is just the product of the probabilities of all of the individual samples. Once again, this is the probability of y in terms of x and w, but x and y are both fixed. They are our training set, and so again, we can re-express this as a likelihood function that depends on w. Also, as in the linear regression case, we're going to choose to use a maximum likelihood criterion to choose our parameters w. So we're looking for a vector w star that maximizes the likelihood function. And again, we're going to maximize the log of the likelihood rather than the raw values in order to avoid issues of numerical stability. So we're going to be using this expression for our maximization, but it's worth noting that the value sigma of xi dot w is, by the definition of our model, our predicted value y hat. And so we could also write the likelihood like this. We'll revisit this in a little while. Before we proceed to trying to maximize the log likelihood itself, one of the things that we're going to need is the gradient of that sigmoid function. We'll first apply the chain rule to split out the reciprocal from the 1 plus e to the minus z squared. So we get these two factors, 1 over 1 plus e to the minus z squared and e to the minus z. We're going to factorise this first term, separating out into two copies of 1 over 1 plus e to the minus z. One of those will then bundle in as the denominator of the second e to the minus z term. That second term we can refactor, so we bring out a factor of 1 plus e to the minus z over 1 plus e to the minus z, and then it becomes 1 minus 1 over 1 plus e to the minus z. And then we note that this expression 1 over 1 plus e to the minus z, which occurs repeatedly in this equation, is just our original sigmoid function. So we substitute that back in, and so we see that the derivative of the sigmoid function has this nice straightforward form. Sigma prime of z is just sigma of z times 1 minus sigma of z. So the log likelihood function that we're going to attempt to maximise looks like this. To simplify our discussion of the analysis a bit, let's consider only a very simplified case. We're going to assume that there's just a single example in the training set, which we'll call x, y. That allows us, for the moment, to avoid subscripting for the separate examples and also to avoid including an explicit sum. And also, we're just going to find a single partial derivative with respect to a single weight parameter, wj. The problem that we're trying to solve then looks like this. We'll expand out each of these terms in turn, applying the chain rule. In the brackets at the end of the second big term here, there's a negative sign. We're just going to move that all the way outside the brackets. Both of these big brackets include this same partial derivative term of the sigmoid of x dot w, so we'll pull those out as a separate shared factor. Using the chain rule on this partial derivative term that we've just pulled out, we expand it into the derivative of sigma of x dot w times the partial derivative of x dot w. Now we just calculated the derivative of the sigmoid a couple of minutes ago, and so we can substitute that in. We've got this sigma dot xw as a product outside the brackets and also as a denominator in the first term inside the brackets, so that's going to cancel. And similarly, there's this 1 minus sigma x dot w term, which is outside the brackets and as a denominator in the second term, so that will cancel as well. While we're at it, let's note that the partial derivative of x dot w with respect to wj is just xj. Because it's a dot product, none of the other terms matter. So our expression reduces to this. Now we're starting to get somewhere. If we multiply out both of these terms, we get this expression. This has a minus y sigma x dot w and a plus y sigma x dot w, so those just cancel. And we get this expression, but the sigma x dot w in this expression is just our predicted estimate y hat, so we can substitute that in. And we can see here that now our expression has simplified nicely. This is the log likelihood derivative that we're looking for in our radically simplified single sample, single weight case. We can straightforwardly repeat this for all of the different values of j, that is to say for all of the weights in turn, and get this expression. If we then aggregate this over a large number of samples in the training set rather than assuming there's only one, then we get this. After all this, we seem to have a really nice, neat expression for the log likelihood gradient. But you need to remember that our model here is non-linear. It has that sigmoid function in it. When we expand it out into its full form and set it to 0 in an attempt to maximise, it turns out that we have an expression that we can't solve. This is obviously a bit annoying after all of that effort, but at least we do have a gradient. And as it turns out, this gradient is concave. So, as we'll see in the next section of the lecture, our problem is more or less solved. Before we get to that though, a couple of asides. First of all of that derivation was quite laborious. And actually, logistic regression is one of the simplest examples of this kind of thing. Manually assembling the algebraic derivatives of complex chains of functions is tedious and error-prone. But actually, the essence of the chain rule, which we're using quite a lot of the time in these cases, is quite straightforward and mechanical. So it really might seem that there ought to be a better way. We'll come back to this in a few weeks' time. As a second aside, we never actually defined a loss function in this case. We just jumped directly to the probabilistic model and the maximum likelihood estimation. It is always possible to just negate the likelihood and call it a loss function. And broadly speaking, that's in fact what we're going to do. Let's just recall this alternative expression for the log likelihood, which we pointed out at the start of the derivation. This expression turns out to have a useful interpretation in information theory. So information theory is concerned, among other things, with the difficulty of representing information and of transmitting it from place to place. How do you encode a message in order to be able to send it efficiently? The difficulty of sending a message depends rather on how surprising it is. If all messages are exactly the same, then all you need is to note that one's been sent. You don't need any content at all. Essentially, you just say ditto and the job's done. This quality of surprise is quantified as the information which is expressed like this. The surprisingness of a whole distribution of messages, that is to say, all of the messages that anyone might possibly want to send, is given by its entropy, a quantity which is calculated like this. This quantifies the overall collective surprisingness of all of the messages, but it doesn't consider the question of transmission. In order to transmit messages, you need to encode them in some way. An encoding scheme characterizes a distribution of messages, and you would like it to be close to the distribution of messages you actually want to send. Ideally, it should make it cheap and easy to send messages that you send often, and only more difficult to send the messages that you rarely or never actually want to send. If there is a mismatch between the distribution implied by the encoding scheme and the actual distribution of messages, then transmission will be inefficient. This distributional mismatch is characterized by a quantity called the cross entropy, which is calculated like this. Here, P is the true distribution of messages, Q is the distribution implied by the encoding. Note the asymmetry in this expression. H of P, Q is not the same as H of Q, P. Reality and the model are not interchangeable. This quantification works for distributions containing any number of messages. But if we consider the restricted case where there are only 2 messages in our distributions, so it's a binary choice, then we get that P z equals 0 is the same as 1 minus P z equals 1, and equivalently for Q, and then the cross entropy calculation looks like this. This should look quite familiar. Remember that P is the truth, Q is an approximation, just like Y and Y hat. And recall that we've defined the outputs of our model, our Y hats, as probabilities. What we find then is that the negative log likelihood is exactly the same as the cross entropy. And in fact, this is probably the most common loss function that's used in classification problems. As we'll see a bit later on, it readily generalizes to multi-class problems, and it also does not depend on any particular functional form for our predictions y hat. It's not restricted to a linear or logistic case. Intuitively, what it measures is a distance between our prediction distribution and the true distribution of the data. One thing to think about there is what happens to it if the prediction is completely perfect or perfectly confidently wrong.